Hey everyone, and welcome back to another one of our studio review videos here. So today we're going to be going over Studio 7, which is the first studio in our three-part series on electrical engineering. And I'm pretty excited to get these videos going because, as you might imagine, this is one of my favorite topics that we'll be doing new in the course this year. And so yeah, with that, I think I'll go ahead and get going. So we're going to go through the first slides a little bit faster. Just because I think these ones are a little bit more self-explanatory as far as the first slides go, and I want to spend the majority of the time where I think the focus should be, which is on the introducing the passive elements and on the problem examples. So yeah, let's go ahead and dive right into it. So the first slide here is just basically introducing you to what electrical engineering is. So just to go over very quickly what's here. So electrical engineering is a very massive field with a lot of different topics, and I've just included some different topics on the slides here. So I've got communication systems and digital signal processing. So you might think about internet communication systems, servers, Wi-Fi routers, all that kind of stuff. You might think of satellites in low Earth orbit now, doing satellite communications. You might think of telecommunications, lots of different stuff going on here. Then we have circuit design, so that includes analog, digital, and mixed signals. So today we're going to be covering analog. And then we'll continue covering analog circuits a bit next time. And there's a lot more, obviously, in analog circuits than what we're going to cover. But we're doing, our little intro. And then we'll cover digital circuits starting in Studio 8, and then we'll really hit it hard in Studio 9. Now, mixed signal circuits deal with analog and digital signals basically on the same board in the same circuit. So that's kind of what that is. So then we have semiconductors and electronic devices. So this is where EE really intersects with material science. So there's a lot of very physics heavy stuff going on here. And yeah, so it could be things like scintillators, it could be photodetectors. We could think certainly of things like transistors. That's probably one of the most prominent examples of this field. Yeah, lots of different stuff here, lots of sensors. And building actual components like transistors. So yeah, if you're interested in material science stuff, this could be a good thing for students to look into. And then another application of this, I just put it on a separate bullet point here, is photovoltaics engineering, so solar cells. And you can see a photo of the International Space Station and its solar array in the bottom right on the slide there. And then computer engineering. So we have things like computer hardware, CPUs, and IC design. So this is where EE meets computer engineering, but the line between computer engineering and electrical engineering is really not so well defined, so I think it's definitely still very much an EE topic, so I wanted to include that as well. And there's a lot of cool stuff you can do in there with classes like 1630, 1640. So microprocessor design, yeah, so you can see kind of an image there on the bottom left. So we might think of something like a Raspberry Pi where you've got, CPU in the middle and then a bunch of peripherals, with GPIO pins that interface with all sorts of different sensors all around. So yeah, so this is just a few topics that I thought of. That's kind of our little intro to what is electrical engineering. So yeah, so as far as the outline goes for these studios, so I kind of hinted at it before, but just to clarify, so today we're going to be doing analog circuits. And the official title of this studio is like DC analysis, but we're really going to be talking about time domain analysis in general, because we want to still introduce sort of what different components do across a range of frequencies, because that is the main thing to talk about when we're introducing these components. We just won't talk about the frequency domain in this studio. So talking about AC analysis and the frequency domain will be in the next studio. And then we'll also do an introduction to CMOS logic and digital logic. So we'll introduce different gates basically. And then in the last studio, which will be Studio 9, our last studio on this topic anyway, we'll talk a little bit about physical transistor structure. So that's our little intro to semiconductors and that branch of EE that I mentioned just a minute ago. And then we'll really hit mostly digital circuits in that one. So we'll build a few different digital circuits and look at some common building blocks like multiplexers, and some cool different little digital circuits like that. So relevant Engine 32 projects, blood pressure cuff has some analog filtering elements and some amplification elements. Solar car, you might think of like batteries, power electronics, you think of like H bridges, all sorts of control stuff. Electric guitar, probably digital signal processing. Friendship lamp actually has some digital circuits components now, so that's a exciting thing. People can look into that more if they want to get more digital circuits. So, okay, so this is our first bit of content here that I'm going to kind of go through rather quickly. But this is just sort of introducing what is AC versus DC analysis, right? So today, like I said, we'll mainly talk about DC analysis, but broadly we're actually going to do time domain analysis stuff as well. But basically DC analysis is the most simple type of analysis. It basically just lets us understand what a circuit does when a constant current is applied to the circuit. So DC, direct current, right? So if I have a constant input, what does my circuit do? So AC analysis, on the other hand, lets us understand what circuits do when a continuously varying current is applied or input into the circuit, right? So think of like a sinusoid, something like that is applied. What does the circuit do then? How does it behave? How does it behave across a range of different frequencies? That's the kind of stuff we're interested in figuring out when we talk about AC analysis. So a good example here, as far as AC alternating current is concerned, is the electric grid. So it turns out AC is much better for power transmission purposes, so you can transmit power much more efficiently with fewer losses over long distance if you use alternating current as opposed to direct current. So your wall outlet has AC, of course. I'm sure that most people will kind of know that, but if you don't, yeah, so your wall outlet's got AC, and then you have a little rectifier circuit. That's how you plug your phone in, right? And your phone and your computer and your tablet or whatever all run on DC. So yeah, little real life example there. Okay, so next here we've got analog versus digital. So I mentioned we're going to be doing analog today and for part of next time, and then we're going to transition into digital, but what does that all really mean, right? So when we think of analog, and I'm sure you guys kind of know this, so I'm going to kind of fly through this. We want to think of things that kind of vary continuously, right? And when we're thinking about circuits, we want to think of things that vary continuously across time specifically. So that's analog. So an analog circuit will vary continuously across time, or an analog signal, I should say, not circuit. And then a digital signal will have discrete steps, right? So an example that might be useful is like an analog versus digital clock, right? So your analog clock has, your hour and minute hand that kind of move continuously across time like that, whereas your digital clock will have discrete steps. It's like 1:30 and then it's 1:31. There's nothing in between, right? So it's just bang, bang. So it's just discrete steps. So as an example of that, you can kind of see it on the slide here, but I'll just draw out, like let's say I have some kind of sinusoid like this. And then let's say I'm going to just identify a few levels here. We'll do like 3 levels, keep this simple. So a lot of times if we're doing some digital signal processing stuff, to make our lives easier, we want to represent some analog signal, which, most signals in nature, so sound waves, stuff like that are analog signals, right? So we want to discretize that analog signal. So we might sample it at specific points here. So something like this maybe. So there we go, and then I'll just draw in my digital version of this analog waveform. So you can kind of see like maybe that would be a very simple, discrete representation of this analog signal, and you can see an example of that on the slide as well. So now the other thing that's on this slide is sort of the visual difference between what an analog circuit might look like and what a digital circuit might look like. So as you can see, our analog circuit in the middle here, this is actually a low pass filter, which we'll talk about next time. But yeah, so this is a low pass filter. We can see sort of these discrete passive elements, resistors, capacitors. We see a voltage source here. So that's kind of the visual look of an analog circuit, and then we have a digital circuit over here, and we see gates. So striking difference there. The reality is the gates are really made up of transistors, and so if you broke it down at that level, then the difference between them might not be so obvious. But at this level, you can see, okay, my digital circuit has gates, and my analog circuit has capacitors, resistors. It might have transistors too, op amps, stuff like that. We're not going to talk about that, but certainly in a project like a blood pressure cuff, you might see some stuff like that as well. So in digital circuits, Oftentimes what we'll see is we'll have this concept of binary. So we'll have 1 or 0. So our high will be 1. So that might be your high power. So VDD, or like to make this concrete, it might be 5 volts. It might be 3.3 volts, whatever that high voltage that your circuit runs at. That might be your logical 1, and then your logical 0 might be ground. So that's kind of the thing we want to think of when we think of the signals passing through a digital circuit. So then obviously analog circuits can have a variety of continuously varying signals input into them. Okay, so that's all for that. So quickly, just to go over some sort of foundational units and concepts that we're going to need for the rest of the studio. So voltage, current, resistance, and then we'll talk about power a little bit too. I'm going to sort of draw an analogy with plumbing or water flow here as I go through these, but just to quickly explain, right? So voltage, we want to think of electrical potential, right? So potential, voltage, same thing. You'll hear me use them interchangeably throughout the studio. And we want to think of voltage like pressure in our water flow analogy. So, you know, I might have a sink where the water is flowing really fast. There's a lot of pressure. And yeah, that might be sort of a good analogy to voltage, you know, just pressure in a pipe. Okay, so then current is going to be flow. So how many electrons are flowing through my circuit? In our water analogy, how much water is flowing through my pipe, right? So now the other thing I want to say about current is that current occurs when we have a difference in potential. Okay, so if I have a potential difference, that is when current will flow. And that's just an important thing to keep in mind, especially when we get into these different passive components that'll kind of come back into play here. But yeah, so that's just an important thing to keep in mind. Current will only flow and will always flow when there's a difference in potential in between two places. So like if you think about a battery, so let's just draw this out a little bit here. So let's think about a battery, something like this. So usually I'll say, okay, there's my ground. So we'll call this 0 volts. And maybe this is a 5 volt battery. We'll say this end is 5 volts, okay? So now if I connect these two with a wire, we know current flows in this circuit. Why is that? Because there's a difference in potential in my circuit, right? So I have 5 volts and I have 0 volts. So my current is going to flow like this, right? So just a good thing to keep in mind, that is sort of when current flows in a circuit is when we have a difference in potential. So now resistance is probably the easiest thing to understand, right? It's just resistance to flow. So we might think of like a blockage in our pipe, right? Same deal in circuits. We just have some resistive element that resists electron flow. Something like a resistor we could use, or it might be something less planned. You know, maybe there's a part of my circuit that got burned out a little bit. That might be a high resistance area. Okay, so those are those foundational elements. Now just to talk about power a little bit. So power takes into account two things in electronics. It takes into account current and voltage. So the equation for power is going to be I times V, so current times voltage. Okay, so it takes in two things. And it's really just the rate of energy transfer, right? So power, you might see it in units of watts, and a watt, right, is just a joule per second. So it's just really a rate of energy transfer. That's what power is. So to kind of bring some concrete examples into this explanation here. So if I get shocked by something, so shocks, an electrical shock can be like thousands of volts. So when you touch a door handle and you get shocked, that could be thousands of volts, but it's super, super low current. So it's still low power. That's why it doesn't kill you, but you feel it, it hurts, right? Because it's a lot of voltage, but super low current. So that might be sort of an interesting example of where you can have super high voltage, but low current, and you get low power, and it's not a super dangerous thing. An analogy with our water flow example. So I sort of mentioned like a faucet earlier. So maybe my faucet has super high pressure, but I can still put my hand under it, right? Because there's not a lot of water flowing there. So that might be low power, even though I have a lot of pressure, I don't have a lot of current. Sort of in the same vein, I could have like a really slow moving river, so there's a ton of water going through there, but the pressure is pretty low because it's slow moving, right? So I can still cross the other side pretty easily. Now, if I have a big raging river that's going super fast, water's flowing super quickly, and it's a lot of water, well, now that's super powerful, right? Super powerful river, it's gonna be hard for me to cross the river. So kind of same thing in electronics, we just wanna think of power in terms of current and voltage together. And then note on units there, watts, right? So another quick note, and it's on the slide. So a thing like kilowatt hours is actually not a unit of power. That is a unit of energy. So that's just a quick note. And the reason for that, right? So watts is energy per time, right? And then we have kilowatts, so that's energy per time, times hour. So that's time. So then the time cancels out, and we see that it's just an energy. So that's just a quick explanation there. Okay, so now Ohm's law, pretty simple here. It's just V equals IR. That's pretty much all there really is to say. It's just the super foundational relationship between those three things that we just talked about, voltage, current, and resistance. So just keep in mind, of course, as I'm sure you guys probably know, these things are related by Ohm's law. And so, for example, in a circuit, usually I'll set my voltage source, for example, like I choose a 5-volt battery, and then I have a resistor across that battery. Maybe that's an LED and then a resistor in series, but in any case, that's a resistive load, right? So that's got a set resistance. So I have my voltage and I have a set resistance. Well, then the current is going to be determined by Ohm's law. So I really choose like two things. I chose that resistance and I chose my voltage source, and then the current is set by the law. Alternatively, I could set my current and then I'd have my resistive load, and then voltage would be determined by the law. So different things to think about here, but just keep in mind that there is this relationship, and we'll come back to this in our example problems, of course, as well, especially when we do nodal analysis. Okay, so now that we've covered some of those basic foundational things, let's really dive into the core of the content that we're going to be talking about today, which is these three essential passive circuit components. So we're thinking about resistors, capacitors, and inductors. And then we'll talk about voltage and current sources as well, which are not passive, of course. But yeah, those will be more simple, and we'll just do that last real quickly. But resistors, capacitors, and inductors, those are the main things we want to focus on in this studio here. Okay, so let's start out with resistors. So what I'm going to try to do for each of these elements is describe how to make them physically, and then we'll talk about what they do and if they vary with frequency. Resistors don't, so that's why we're starting with this one. It's kind of the easiest one, but we'll talk about that as well. So we'll just try to go in that order here. So first, what is a resistor, right? So resistors, basically every material has some sort of resistance, and we'll call that resistance R, and it's going to be expressed in ohms. And there's our symbol for ohms here. Okay, so every material has some resistance, except for maybe superconductors. But yeah, so resistors basically just cause a voltage drop in our circuit, right? So anytime I want to regulate voltage or have a voltage drop in a circuit, that's where I'll see a resistor used. So you guys have probably maybe used a resistor if you're doing like some Arduino project and you wanted a little LED in there, then a lot of times you'll put a resistor in series with your LED. Super common thing to do, just so that you drop some voltage across your resistor so you don't blow up your LED. So that's like a super common example of maybe where you use a resistor in a circuit. And of course there's lots of other examples, and resistor voltage dividers. You can use them to set gain on op amps, but we won't get into all of that, but just some sort of example applications where you might see a resistor. And then how to make a resistor physically. I just have one example here, which is wire wound resistors. There are other types of resistors, of course. In microelectronics, you might see something like polycrystalline silicon used as a resistor. Basically, there's just lots of different resistor types, but this is just sort of the most common one maybe that you'll see in the lab a lot, is these axial wire wound resistors. And so basically how these work is you'll have an insulative material as the core, and then you'll have a conductive wire that you wrap around, and you can control the resistance based on the material that you use for that wire, and also the pitch and the number of coils. So that's one example, and you'll see You can get some super high power resistors like this big 100-watt resistors that are also wire wound in the same sort of way. So just super common resistor type. Thought I'd throw that in there just so that start getting an idea of like what each of these elements actually look like physically and how they're made. But yeah, basic thing here that we need to know for this studio, resistance, we'll just call it R, and it's measured in ohms. So that's it. It doesn't vary with frequency. It's super simple. And so that's kind of why we're starting with this one. So yeah, for our purposes, resistance will be a constant. Okay, so now that we've talked about resistors, let's move on to capacitors and inductors. So we'll start with capacitors here. So I'm going to start off with just what a capacitor kind of is and how we make it, right? So same deal as resistors. So basically the idea with a capacitor, right, is that we can store electrical energy by accumulating charge between two plates. So the idea of a capacitor is I store energy in the form of charge. So now how this looks physically, right, the simplest form of a capacitor is a parallel plate capacitor, and that's the model you'll see probably used most commonly. And so you can kind of see an image here on the slide that I'm sort of circling here. But basically, yeah, so I just have a conductive plate, and then I'll have some dielectric or insulative material, and then I'll have another conductive plate. So it's just two conductive plates with a dielectric / insulating material between them. And if I sort of apply a voltage difference between those plates, they'll start accumulating charge. So let me sort of just draw this out a little bit. So we've got our two plates here, and we've got some dielectric in between. And let's say I apply some voltage here. We'll call this like 1 volt, doesn't really matter for this example. But basically I'll start accumulating charge on my capacitor plates. And so that's what a capacitor is. So it stores energy using this mechanism right here. It just stores its charge on these plates. And then if I do something like this, I unconnect my voltage source and I maybe make a wire connection between the two plates, then that charge will get released. And so let's say, maybe I put a resistive load right here to drop that charge. So now we have some kind of RC circuit. Basically what you'll see is our voltage across time sort of does something like this. So it'll have this exponential decay across time when I make a wire connection with my capacitor. So yeah, so that's kind of what a capacitor is. And yeah, so I mentioned just a minute ago, we have two parallel plates and a dielectric between them. How I make this in practice is I do that. So I have my two plates with the dielectric, and then I just roll them up. That's how I make an electrolytic capacitor, which is that orange capacitor diagram you see on the slide, that third image. And the thing about electrolytic capacitors is that they work better at lower frequencies. And so that's what they're good for. If we have a low frequency application, we'll often see electrolytic capacitors. But the thing about them, right, is that they're electrolytic, so if you hook them in backwards, they break down or explode. So you have to be careful with those ones. But another type of capacitor I thought I'd mention that you can see in the last fourth image there. So there's the electrolytic capacitor in that fourth image, which is the black one. And then the little yellow one is a ceramic capacitor. So these are smaller. They're usually lower capacitance than electrolytics. And we use them for high frequency applications. So if you want a good performance across a wide range of frequencies, oftentimes you'll see electrolytic and ceramic capacitors placed in parallel. So that's just a quick note, different types of capacitors for different things, and that's kind of gives you a little bit of an idea of how they're made. There's a little bit more than that, but that's sort of the basic idea of how a capacitor is made. Okay. So yeah, we talked about the parallel plate capacitor. Now let's get into the most essential discussion, which is how capacitors behave across different frequencies. So the first thing we're going to start off with, because we are talking about DC analysis in this studio, is, well, what happens when a capacitor is placed in a DC circuit? So if we just have DC domain, then capacitors basically look like open circuits. They just don't look like anything. They're basically not there at all. And if you think about that, that kind of makes sense, right? Because a capacitor, like I said before, is just two plates that aren't touching. They have an insulative material in between, so there's no connection there. So at DC, nothing's going to happen. It's like that capacitor isn't there at all. You might as well just ignore it or take it out of the circuit. It's not really doing anything as far as we're concerned from a mathematical perspective when we're analyzing circuits. The reality is it has that charge buildup, and so it's accumulating some energy there. But as far as we're concerned, it doesn't really do anything. It's just an unwired connection. So DC capacitors are pretty boring. So now at low frequency, capacitors are going to continue exhibiting similar behavior. So they're basically going to look like an open circuit. So it's basically like capacitors aren't there at low frequency / DC. So super low frequency / DC, open circuit. Now, at higher frequencies, so super high frequencies, capacitors start to look more and more like a short. So they just look like a wired connection, closed circuit. So capacitors look like open at DC and low frequency, and they look like wires at high frequency. So just a short in the circuit. So basically, that kind of gives you hopefully some kind of intuition about why that's happening, because, like I described, the plates aren't even touching, so at DC that makes sense. Now let's look at this mathematically, which will hopefully give us a clear view of why we see this behavior. So first thing we need to introduce, so I'm going to derive an equation here that we'll then analyze a little bit. So first thing we need to understand is this concept of charge. So I talked about charge building up on these two plates. Well, what is charge? So it turns out charge is just the time integral of current. So it's just the integral of current with respect to time. So now resistance, we had R for our resistance in ohms. So capacitors will have some capacitance, and then inductors will have an inductance. So capacitance is just some constant, C, and capacitance is defined as charge, Q, over voltage, V. So that is what capacitance is. So now let's start deriving an equation. Basically the goal here, what we're trying to do is have an equation that relates the voltage drop across the capacitor and the current flowing through the capacitor. So we're basically trying to derive an equation that has voltage and current so that we can understand the capacitor's behavior across frequencies. So with these two pieces of information, we can derive that equation. So let's move some stuff around. So we've got CV equals Q, and then let's plug in our Q equation. So we have CV equals the integral of I dt. And then let's just use the fundamental theorem of calculus to get rid of the integral. So remember I said C is a constant, so we end up with, on this side to the left, is just C dV over dt. And then over here to the right, I've canceled out my integral, so I just have I. So there's our equation that relates current and voltage for a capacitor. So a little bit of calculus, but not too involved. So we get our equation. So C dV dt. There we go. And now we have an equation that does exactly what we wanted. So now let's talk about what we can sort of get out of this equation. So now what we see here, let's just go back to the same presumptions we had before, which is that a capacitor looks like an open circuit at DC and low frequency, and it looks like a wire at high frequency. So if my input, so let me just draw out this. So let's say my input is in orange. Let's say I have a DC input, okay? Let's say that is 5 volts, whatever, doesn't really matter. So if I have a DC input, well then dV over dt, this term, goes to 0, right? Because it's not changing, it's just a constant. So the derivative of 5, so d dt of 5 is just 0, right? So our current is 0. So we see, in fact, that yes, a capacitor does in fact look like an open circuit, meaning there's no current flowing through it at DC. And at low frequency, we're going to have dV over dt is going to have some very small value, so there's basically going to be no current. So we see that behavior. So now that kind of makes sense mathematically. So that checks out. So now what happens if I have super high frequency moving through my capacitor? So let's say my voltage is going like this across my capacitor. Well, now we have rapid changes in voltage across time. So we look at these slopes here, these super high slopes that I'm sort of outlining here in red, and we recognize that dV over dt is going to take on a pretty large value with those rapid changes in voltage over time. So then we see that we get a large current output or a large current flow through our capacitor if I have a signal that has a voltage changing very rapidly in time. So that would be like a high frequency signal. Then I see that my capacitor starts to look more and more like a short or a wire because there's current and it flows through there easily. So hopefully that kind of explains both intuitively and mathematically what's going on with the capacitor. So yeah, I think that's all that there really is to go over there. So now let's talk about inductors. So an inductor is basically just a coil of wire, right? So you can see that on the slide here in the bottom right. So you just see that coil. So draw that out, it's just a coil of wire. That's really what an inductor is. And the whole idea behind an inductor is that we can basically resist changes in current. So that's basically what an inductor does. An inductor stores energy in a magnetic field when we have current flowing through it. And because of that, an inductor is really useful for resisting rapid changes in current flow. So let's talk about kind of why that is a little bit here. So basically, when we have a current change through the inductor, my magnetic field, because we talked about before, right? An inductor is storing energy in a magnetic field. So when current flows through my inductor, I have a magnetic field. When I have a change in current, my magnetic field changes. So let's say I have more current suddenly flowing through my inductor. Well, then my magnetic field gets stronger and it starts to expand, right? Now, when that happens, I have a magnetic field that's changing in time. Well, that is going to induce a potential difference across the length of my inductor. So it will induce different potentials across the length of my inductor as that magnetic field is growing stronger. Now, we talked about before when we introduced the concepts of voltage, current, and resistance. We talked about current. We said that current flows in an electronic circuit when we have a difference in potential or a difference in voltage, right? So now what I'm saying here is that we are having a growing magnetic field, and then across the length of the inductor, I'll have different potentials because that magnetic field will induce those different potentials across the length of the inductor. And what that's going to do is cause current flow. So now I have a current input, and then the B field grows, and I have potential differences. That's going to have a corresponding current that's going to flow in the opposite direction and cancel out my input current. So that's how an inductor is physically able to resist changes in current. So hopefully that explanation makes at least some sense there. I hope I explained that as well as I could. But yeah, so that's physically what's going on with the inductor. So now let's talk about what this looks like in terms of different frequencies. So in the DC domain, an inductor is just a wire, okay? And that makes sense, right? Because we just said before at the beginning of this whole introduction to inductors that an inductor is just a coil. And that's all it is. It's just a coil of wires, just a wound up bunch of wires. So in DC, that's what it looks like. It just looks like a short. Now in AC, so as I get more changes in current, my inductor starts to look more and more like an open circuit. And that makes sense based on that explanation we just went over, right? Because as my current changes, right, that inductor, because of that change in magnetic field and the induced potential difference and then the resisting opposing current flow, well, at high frequency, that's what the inductor does. When the current changes, my inductor starts to resist that and looks more and more like an open circuit. So we see kind of a duality here between the capacitor and the inductor. So, the capacitor at low frequency looked like an open circuit. The inductor at low frequency looks like a closed circuit. The capacitor at high frequency looked like a closed circuit. The inductor looks like an open circuit. So now let's go over some of the math that kind of makes this make sense. So we got the intuitive side, now let's get the mathematical side. So I'm not going to derive all this stuff like I did for the capacitor, because I think the capacitor one is a little more instructive than this would be, but I am going to introduce the equation here. Okay, so the equation here is Vt is equal to L di dt, and L is the inductance. So I'll just make that note. So this is the inductance. Okay? And then the other equation I want to introduce that's a little less important, but just sort of background information for you guys. So this is the most important thing right here, this equation. Now, sort of an auxiliary bit of information is that the magnetic field, or the B field, so B is given by mu naught, which is the permeability of free space, times N times the current I over the length of the inductor L. Yeah, so that's the equation for the magnitude of the magnetic field here. So basically what we see here, right, the first thing I want to point out with this equation is that as my current gets stronger, my magnetic field gets stronger. So they're directly proportional here. So what I was describing before, where I get a larger current and then my magnetic field expands, that kind of makes sense with that equation now. So we see that they're proportional. So now the most important equation here, so let's talk about why this sort of makes that explanation make sense as well. So we see V of t, so this is the voltage difference across the length of the inductor, is equal to the inductance times di over dt. So now for DC, di over dt, right? So DC, right, direct current is just constant current. So now di over dt is going to go to 0 if we have direct current. So this goes to 0. So what does that mean? That means that the voltage difference across the length of my inductor is 0. Well, what that means is that the inductor doesn't cause any voltage drop. So if I have 5 volts at this point at DC, so if that's 5 volts, let me move this stuff down a little bit, make some room. So if that's 5 volts at DC, this will also be 5 volts, and we see 5 minus 5 is 0, therefore V is 0 because that's the voltage drop. So just to clarify, it's not that the voltage going through the inductor is 0, it's just that the difference in voltage is 0. Okay, so we get 5 volts in, 5 volts out. So what does that look like? That looks like a wire. So if I had a resistor there, then I would actually get a drop. Maybe I get, instead of 5, I get 2 volts. But that's not what I get. So at DC, di over dt goes to 0. That means V goes to 0. So the voltage drop is 0. That looks like a wire. So that checks out with our intuitive explanation that we had before, right? Where we had at low frequency in DC, it looks like a closed circuit or just a short or a wire. So that kind of checks out. So now we see that, in fact, yeah, we have no voltage drop at DC. So that's exactly what a wire does. It doesn't have any voltage drop, ideally. So there's that. So now, as we get higher and higher frequencies, so di over dt starts to take on a larger and larger value, my V of t, that value gets larger and larger and larger. So now we see a larger and larger voltage drop across the length of my inductor. So what does that mean? That means that my inductor is looking like a larger and larger and larger resistor. And if I have a resistor with infinite resistance, then that's the same as an open circuit, right? So if I have a super large resistance, that's basically an open circuit, which is exactly what we said before. So hopefully that makes some sense, both from an intuitive standpoint with the whole expanding magnetic field and that explanation that I gave before, and then also from a mathematical standpoint now that we can see the equation here. Okay, so that was actually really the most complicated content in this studio. So last thing that we need to introduce before we get into just doing some math with parallel and series components and nodal analysis stuff, some example problems, is this voltage and current sources. So This is pretty simple, I think. It's just like a battery. Basically, you can think of your voltage or current source just like a battery. Batteries, probably more inclined to think of that as a voltage source because you'll buy like a 9-volt battery, right? You don't buy a 5-amp battery, you buy a 5-volt battery, or a 9-volt battery. So yeah, so a voltage source is just kind of like your battery. Basically, it's the same thing that I said before, right? So you'll either choose to have a voltage source, or you'll choose to have a set current. So set current or set voltage, you get to choose. Usually people choose to set a voltage, so that's why you see, commonly like batteries are rated in volts. And then you'll have your resistive load, and depending on whether you chose voltage or current, the other one will be set by Ohm's law. So yeah, voltage and current source is pretty simple. It's just like a battery basically, right? It's just the thing that's supplying power to your circuit. Okay, so now that we've gone through all of our elements, let's just talk briefly about some other essential circuits laws that we're definitely going to be needing to know to do our example problems here. So the first one is KCL, or Kirchhoff's current law. So basically what we have here is that the sum of currents coming into a node will be equal to the currents coming out of the node. Okay, and you can kind of see an example of that on the slide here. So now quickly, what is a node though? So let's just look at our series and parallel image here. So basically a node is just going to be a connection between two circuit elements. That's what a node is. So it's really just a wire in practice. You can see I've sort of outlined the nodes in different colors here on this slide. So we've got this blue represents a node, and the red is a different node, and green is a different node. So you can kind of get an idea of what a node looks like. It's just what I was saying before. It's just a connection between two elements. That's all a node is. So now, just sort of redrawing what's on the slide here, but to make this a little more concrete, what KCL is saying here. Basically, if I have a node like this, and I've got a bunch of currents coming into the node, and then I've got some wires leading some currents out. Basically what we say here with KCL is that I1 plus I2 plus I3, so those are all the currents coming in, right, is equal to I4 plus I5. So sum of currents in is equal to sum of currents out. That's all KCL is really saying. And we can do some really useful stuff with this, it turns out, when it comes to nodal analysis, which we'll get into an example problem in a few minutes here. So that's just something to keep in mind. So that's kind of what we're talking about when we say KCL. So I'm gonna leave that here actually. Just put KCL. Okay. So there we go. So now the next thing we need to talk about is what different elements behave like when they're put in series versus what they're behaving like when they're put in parallel. So first things first, what is series and what is parallel? So this is something that a lot of people probably might have an idea about, but just to define it concretely. So series is two components are in series when they share just one node. So if they share just one node, then they're in series. So they have just one connection. That's what we're looking for. So you can see here in this image, these elements share just this red node, right? This red wire. So they're in series because they share just one node. So the blue and green nodes are different, and so we say they only share one. So now in parallel, the elements share two nodes. They share both of their nodes. So these two lights, we say they're in parallel because they both share the blue and red nodes. So that's what we're talking about when we say series and parallel. And it's really easy to see in this image. The thing is, sometimes when you're given a complicated circuit, it's kind of hard to just see, oh, these are in series, they're in parallel, unless you remember that definition. So just keep that in mind, this node definition. So series, one node, parallel, both nodes, okay? So just keep that in mind. So now, let's talk about how we can simplify resistors in series versus parallel, and capacitors and inductors, same deal. So it says it on the slide here, but let's go through it in more depth here because I just put the equations for resistors because there's so many equations if I start listing them all, but they're really just the same thing. So let's start with resistors. So resistors, and we'll start with series. So things in series. So resistors. So what happens if I have resistors in series? How can I simplify that? So we have R1 and R2, and then we could have more, but you'll get the idea with just these two. So we can create an equivalent resistance. I'm going to call that REQ by just adding these two components together. So in series with resistors, we add. So R1 plus R2, and if I had more, like another one here, then I would just add that on. So I'm going to keep it to just these two, but that's what you would do if you had more. So the equivalent resistance, we can basically, what we're saying here is we can replace this situation is entirely equivalent to just one resistor with the value of REQ, which is just R1 plus R2. So we can basically replace R1 and R2 with just one resistor that is equivalent to the sum of R1 and R2. So that's what we're saying here. Okay? And we'll do some example problems with that. So now that's resistors. Let's talk about inductors. So it turns out inductors and resistors are going to sort of share the same equations for series versus parallel. Then capacitors will be the oddball, essentially. So inductors, let's draw this out. So two inductors in series like this, and they'll have some inductance L, L1 and L2. So LEQ, L equivalent, is going to be L1 plus L2. Okay, you just add them up just like the resistors. Now I said the capacitors were going to be our oddball ones. So capacitors will do something a little different here. So we'll have some capacitors in series like this, C1, C2, those are the capacitances. And for this one, I think it's instructive to actually say what happens if there's more than two. So just to be super clear, we'll say ... So that's just however many you want up to Cn, some Cn, okay? So what that's gonna look like is CEQ is actually going to be 1 over C1 plus 1 over C2 plus ... plus 1 over Cn. Okay, so that's actually our equation for the equivalent capacitance. So it's 1 over the first capacitance plus 1 over the second capacitance plus blah, 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 whatever, keep on going, okay? So there's that. So that's for series. Now let's talk about parallel. Okay, so now everything's going to flip. So basically, the resistors are going to start using this equation here, and inductors, and then the capacitors will be our simple one this time, and we'll just add. So that's what's going to happen, but we'll write it out explicitly. So let's talk about resistors first. Move this down a little bit. So put resistors. So resistors. Okay. There we go. Boom. They're in parallel. R1, R2. And so REQ is just 1 over R1 plus 1 over, or I'm sorry, 1 over R2, okay? And same deal as we had for the capacitor, right? If I had more resistors, like let's say I had another one here, R3, then I would just add that in, 1 over R3, okay? So you just keep on going, however many you have in parallel. All right, so now let's talk about inductors. And they'll do the same thing. So let's draw out our little inductors here. L1, L2, boom. So LEQ, the equivalent inductance, is just that same deal. 1 over L1 plus 1 over L2, okay? And so on. And capacitors, finish it off, are actually easy this time. So capacitors in parallel, C1, C2. So C equivalent is just actually C1 plus C2. And then if you add more in parallel, then you just add the rest of those, okay? So hopefully that clears that up. That's what these different components do in series versus parallel. Okay. And then the very last concept on this slide is just what ground is. So I've already sort of talked about that a little bit in some of the things I've drawn. But basically, ground, right, is just a point in the circuit that I choose to represent 0. So you'll also hear it called a reference point. So it's just some point that I conveniently choose to be 0. So usually, like if I have a battery, you know, something like this, and this is the positive end of my battery up here, so plus, minus. Usually if I have something like that, that gives me a good place to put ground. I'll usually put it here, so I'll say that this is 0 volts, and if I have a 5-volt battery, that makes this conveniently 5 volts, because really what we say when we have a 5-volt battery is that the difference between the battery terminals is 5 volts. So in circuits, we're always talking about differences between things, so that's why we have this concept of ground, so that we can conveniently call something 0, so that it's just easier to talk about, oh, this is 5 volts. So it's really 5 volts. The correct way to say it is 5 volts with respect to this reference node. So that's why you call it the reference, because it's, you know, 5 volts with respect to what? You know, 5 volts with respect to this node, which is we're calling ground, and we're conveniently saying it's 0. If you wanted to say this ground was 1 volt, I don't know why you would do that, but if this, you wanted to have all your grounds be 1 volt, that's fine. And if you had a 5-volt battery, then this would become 6 volts, and that works out. Don't know why you would do that, because that makes your life more difficult, but you could. So yeah, that's all the ground is, just a node that we conveniently choose to be 0. And we reference all the rest of the nodes based on that one. Okay, so now that we've covered all the essential content that we need to go over in this studio, let's go through some example problems. So we've got 4 example problems here. 1 is nodal analysis, that's the first one, and then the other 3 are going to be computing equivalent resistances, inductances, capacitances for series and parallel connections, okay? So let's go through this first KCL one, which we'll do in MATLAB actually. So what we're looking at here is this ladder circuit with a bunch of resistors, and we basically are asked to compute the voltages at nodes A here and at node B, okay? So that's what we're trying to find. So let's just call this voltage VA, call that voltage VB. All right, so now how do we do that? So we know that the current coming into and out of each of these nodes will sum to 0. So now what we can do with nodal analysis using KCL is we can first assume that all of the currents are coming into each of our nodes, and then set that corresponding sum equal to 0. So let's kind of see how this works here. So first of all, this node, right, is at V, which we see here. Well, let's make that explicit. So we'll call this the ground location, because this is what I was talking about before, where this is a nice place to put ground because we've got the negative end of our voltage source here. So we'll call that ground, and then that makes this V. And so in this case, what we'll do is we'll say, okay, we'll call this I1, this I2, and this I3. So we'll say that I1 plus I2 plus I3 is equal to 0. Now, why is that true? Well, we know that, we've assumed that all of these currents are coming into node A, when in fact some of them are coming in and some of the currents will be going out. That's the reality, right? So now, intrinsically then, some of these will be negative because we've assumed they're going in, but in fact it's the opposite way, therefore the current will be negative when we compute this. So for example, like I3, let's say that turns out to be negative, well then this equation makes a lot more sense, right? Because we would have I1 plus I2 is equal to I3, you know, if that were the case, something like that, okay? So we have that, but we're still not that close to finding that voltage at node A. So how do we do that? Well, let's use Ohm's law, right? So we don't really have these current values, but what we do have is what we're looking for, VA, and we know that this node over here is V, and we know that this node over here is VB, and we know that this node down here is 0, okay? And we have set resistances. So by Ohm's law, we can say that the voltage drop across this resistor over the resistance is equal to the current through that resistor. So I1 will then be V minus VA over R by Ohm's law. So that would be I1, for example. Okay? So let's just write that out for each of them. So that's I1 plus, let's write out what I2 would be. So I2 is going to be 0, right, minus VA over 2R. And then I3 is going to be VB minus VA over R. And that all gets summed to 0. So that is the basic principle behind nodal analysis. That's basically what we're going to do every time. So now I'm going to erase this I1, I2, I3 notation here. Okay? So you can, when you're first doing this, start out with actually drawing out the currents and then figuring out what that equates to in terms of voltages and resistances. But once you start getting going here, and you get the rhythm of it, you can just sort of skip that and go straight to, okay, it's far voltage minus near voltage over resistance, and then you just move through. So let's do that for B. So let's go a little faster here. So for B, I'm going to start with this. So we have 0 minus VB over 2R plus, and then let's go here, VA minus VB over R equals 0. So now, the reason I knew to also analyze what was going on at node B, right, is that we have two unknowns here. So we have VA and we have VB. But if I would have stopped here, we wouldn't have had one equation and two unknowns. So I needed another equation here. So naturally, I'm going to analyze what's going on at my second node here. So basically the idea is I go through my circuit, I identify nodes of interest, and then I just use KCL and write out an equation like this, and then I solve my system of equations to get my nodes that I'm interested in, and there we go. We can solve for all of the nodes in any circuit now using this method. So now we could solve this out by hand. This system isn't too complicated, but I think it's better to do it in MATLAB. So with MATLAB open here, let's start writing out our system of equations here. So first things first, I'm going to say clear all, just some standard housekeeping stuff, clear all CLC. Pretty optional to do that, really, but we'll just run it anyway. And you can see I've already got some stuff in here. So I'm going to go ahead and clear that out. Those are actually the answers, so I've already run a different script to test this out, but clear that out. So, okay, so yeah, so setting this up, so solving the system, we basically want to write out sims and then our unknowns. So our unknowns here that we're searching for are VA and VB. Those are the things we want to solve for. Now the weird thing here, which is a little bit maybe unusual if you've never solved symbolic equations or found symbolic solutions in MATLAB, is that we also need to write out our symbolic variables that don't have specific values. So those would be R in our equation, and then we also have V. So we need to write those out as well so that MATLAB can solve VA and VB in terms of R and V. Really, it turns out that R cancels and we'll just solve it in terms of V, but nevertheless, we want to write out those. Okay, so let's write out our first equation. So our first equation is V minus VA, right, over R, plus 0 minus VA over 2 times R. And then plus VB minus VA over R. All of that equals 0. Double equals 0. And then we have our second equation. So we'll have VA minus VB over R plus 0 minus VB over 2 times R. Okay? And then double equals 0 again. Okay, and now I'm going to make this a little cleaner by creating some arrays for my equations and variables that I can pass into my solve function. So we're going to say equations, equation 1, comma equation 2 here in the square brackets. And then we're going to say vars for variables, and we're going to set up VA, comma VB. So those are the things we're going to pass in here. Now, so that I can save the value in VA and VB, I'm going to say VA, comma VB equals solve. So solve, the return values from solve will be stored in VA and VB now, and we're just going to pass, as it says, equations and vars. And that's it. So now we can run this. Here we go, give it a second here. And there we go. So now we get VA, turns out, is 6V over 11, and VB is 4V over 11. And that's it for this problem. Okay, so that was the end of our MATLAB problem. The rest of these we can just do by hand. So the first example here is with resistors in parallel and series. So this is actually the same circuit that we just looked at before, but this time the question has changed. So we want to represent this circuit as just a voltage source and a resistance are equivalent. So just one resistor. So basically we're trying to get this circuit to look like this. That is our goal, and we want to find REQ, okay? So we can do that using the concepts that we just learned about how resistors simplify when they're in series and parallel, right? So first thing I identify here, I kind of see that these two resistors are in series, right? Because they're sharing this node right here. So we can kind of simplify the circuit right off the bat. So our first simplification that we'll make here is this. So we've got R, we've got this is going to be 2R still, and that resistor, those will add up because they're in series, so that'll be 3R, okay? And now it's clear that these two resistors are in parallel, so we can simplify this again. So we see that if we take these two, so the equivalent resistance there will be 1 over 1/2 plus 1/3, and that's going to be 6 over 5, okay? So let's draw that out. So there's R, and then that resistor right there that we just simplified down is going to be 6 over 5R, okay? And now these two are in series. And so finally, we can compute REQ is just R plus 6 over 5R, and that is just 11 over 5R. So that is the answer to this question. Okay, so let's move on to the next one, which will deal with capacitors. So there's one for resistors, one for capacitors, and one for inductors. So here's our capacitor one. So we're trying to do the same thing here. We just want to find the equivalent capacitance between terminals A and B. So these ones have specific terminals here, A and B. Okay, so this problem is actually pretty quick. So the first thing we see is that this group of capacitors, this group of capacitors, and this group of capacitors, each of the capacitors in those groups are in parallel, right? So what we can do is, remember, capacitors in parallel actually just add, so this is pretty easy. So we can simplify this down pretty quickly to something like this. So here's terminal A, we'll have one capacitor here, capacitor here, and there's terminal B. So now we just add. So 1 microfarad plus 1 microfarad is 2 microfarads, and then 2 plus 2 plus 2 is going to be 6 microfarads, and then we've got 3 microfarad capacitors, which is going to add up to 12 microfarads. Okay? So now these ones are in series now. So now we just use our series equation. So it turns out the CEQ is going to be 1 over 2, this 1 over 6, this 1 over 12. And if you simplify all of that down, you're going to end up with 4 over 3 microfarads. So that is the answer. So it looks pretty complicated, but it's actually pretty quick. And there we go. All right. So now our final example, which might take us, well, still won't take us too long, but it's slightly more confusing possibly. So this is where it comes back to, okay, well, what is a node, right? Which things in the circuit are a node, and that'll help me see what's going on more easily. So it's drawn in a very confusing way, but let's just go back to that definition, right? So let's identify some key nodes. So we have this weird situation on the ends here with all of these inductors, right? So they're all connected in this weird way. What's going on here? Well, let's take a look. So here's a node, okay? And I'm gonna use different colors. Here's another node, okay? So you can see what's happening here maybe now as I draw this out. And there's a node. Okay, there's that purple. So what do we see here? So we see this group of inductors here. These three share both nodes. So they're all in parallel. So it's hard to see the way that this is drawn, but when you start identifying nodes, it becomes a little bit more clear. So these three inductors here, they share the red node and the blue node. Okay, so let's kind of redraw this circuit in a slightly more easy to follow fashion, okay? So let's just draw out all those inductors there first. So there's my 3 inductors that are going to end up being in parallel actually. Now we can see that. And all the inductors have inductance L in this problem. And then we have this inductor and we've got this inductor. So let's draw those in to connect our 2 groups of parallel inductors. So this has L and this has L. Okay, so this is starting to look a little bit less bad, hopefully. And we can redraw our terminals right here because they're on those nodes. So we can just flip them around. There we go. Because remember, this terminal is actually just on this red node, so I can equivalently draw that one there. And this one here, same thing, okay? So if that's more, simple for me to see, no problem, I can redraw them there. So now that looks a lot simpler. So we took this crazy circuit and we just identified nodes, and now we drew this in this more standard way that makes it easier to see things. So now, like I said before, this group and this group have a bunch of parallel connections. So what is the equivalent inductance of one of these groups? Let's figure that out. So turns out here, we're gonna have 1 over L plus 1 over L plus 1 over L, right? And what's that gonna be? That's gonna be L over 3, right? So that's what we find out. So the equivalent inductance of those groups is just L over 3. So let's redraw our circuit now with that modification. So here we go. There we are, and then there's one more inductor here. There we go. So now these ones have inductance L, and these ones have L over 3. So we replaced those groups of parallel inductors with these two inductors with value L over 3 for the inductance. Okay? And now we see, oh look, this big group of 3 all have series connections. So I can just add those up. So we've got, L over 3 plus L over 3 plus L. And that's going to get me to 5L over 3. Okay? So now, final simplification there. Now our circuit looks like this. So this is still L. We still haven't modified this guy up here. But now we've modified those 3, combined them. So that is 5L over 3. And now, these are in parallel. So that's our final step. And in fact, we see that LEQ. So we have 1 over L plus now 1 over 5L over 3, which is 3 over 5L, right? It's just going to come out to 5 over 8L. Okay, so there is our final answer. So that one might look a little bit confusing, but in reality, once you identify all the nodes, it all becomes pretty clear. Okay, and that is actually it for this studio. So I hope that that helps. Now that we walked through all of this content, we've gone over the each of those 3 passive components: resistors, capacitors, and inductors, in quite a bit of detail in the time domain. And next time we'll talk about the frequency domain. So we did a little bit of calculus today to talk about all those components in the time domain. The frequency domain will allow us to use the same equations, but with phasor notation, which allows us to get rid of the calculus component and maybe see these things a little bit more easily in a different, kind of in a different way. So yeah, we'll talk about that next time, and I hope this was helpful. And yeah, I'll see you guys on the next one.